All right, a very good morning, class. Greetings of the day. So let's start with the topic of the chemistry. We have been discussing since last 2-3 lectures the solid state, and we have discussed the basic concepts of solid state, the unit cell, the crystal lattice, and the unit cell, the different 7 type of unit cells on the basis of which we have derived our different particular table on the basis of their axial angles and their alpha, beta, gamma, the axial, the edge length. Okay. Rather than we have studied, there are 3 different type of unit cell on the basis of atoms present over there. Okay. In the last lecture, I have given you a brief idea about this, and I have told you a question that what would happen if a unit cell is repeated over and over again and again. That means a unit cell is not present only in the crystal lattice. There are so many unit cells on the crystal lattice which are present over also, in the downside, in the left hand side, in the right hand side too. So now we are going to check out that what in actual these number of atoms are shared by a whole unit cell. Okay, so let's start. We have 3 different type of unit cells, that is the primitive, the body centered, and the face centered. In all 3 unit cells, we are going to discuss how many number present. So let's start with our primitive unit cell, or simply we can say it simple unit cell. Okay, so let's start. You know very well that in a simple unit cell, as you know, there are some crystal points, sorry, some lattice points, and these points are nothing, these are the constituents, atoms or ions present over there. In simple unit cell, there is all the atoms present only and only in the corner. Not any kind of atom are present other than the corner, beyond than the corner. Okay, but what actually happens, we are going to assume our atom in chemistry, in the whole chemistry, not over in the solid state, in the whole chemistry, we are assuming our atom as a sphere. Okay, now I am saying, please imagine this in the 3 dimension, that this unit cell is completely occupied by the same unit cell over here again. Let me, just shed it over to recapitulate it or just to highlight it. Okay, same as it is, this is present over there too, and in the right hand side also, in the left hand side also, in the upper two, in the lower two, and so on. Okay, so now let's assume this point as this sphere. We have total 8 number of atoms in a unit cell, and each atom is completely shared by, or we can say completely surrounded by, different unit cells. So this is a kind of shifted, this is a kind of cut out by different unit cell. A unit cell is sharing this one, a unit cell is sharing this one, and this one. The 4 we can see from this side, the 4 are behind the side, because this is 3 dimension. So in short, I just want to say that each atom, each cell representing here is shared by 8 unit cells. This is 3 dimension. If it seems to imagine a little bit difficult, please imagine this in this way. We have total number of 8 atoms in a unit cell. Each atom is shared by 8 unit cells, because there are 8 different directions present all over it. Okay, so we can say each atom in a unit cell is shared by 8 different unit cells. First point. Now, if 8, I'm sorry for that. If each atom is shared by 8 unit cell, what would happen? And what would be the share of this unit cell, this particular unit cell which is shaded? This would be 8 multiply 1 by 8. Why? Because there are also 8 atoms. Okay, so in short, I would say that since only 1 by 8 of atom belongs to a particular unit cell, let me write to just make it more effective to understand you. 1 by 8 of an atom actually belongs to a particular cell. Okay, and how many total number of atoms we have? We have total 8 number of atoms. So 8 multiply 1 by 8, that would be equals to 1. A number of unit cell is shared by only 1 in a unit cell. That means there is only one number of atoms which an actually primitive unit cell has. Number of atoms in primitive unit cell. See class, now you want to say that, ma'am, this is totally different concept, as we have seen that there are 8 different corners and you have said that each corner represents 8 different atoms. That is quite true. But I am saying that imagine it in 3 dimension. Imagine this unit cell covered by in all the direction, in all the faces, by 8 different unit cells. Because there are 8 atoms, so this is shared by 8 different atoms, as I have shown. So 1 by 8th of an atom actually belongs to a particular cell. So in short, we have 8 multiply 1 by 8 equals to 8, 1. So number of atoms that is present in primitive unit cell is only equal to 1. That is the first concept, that is very important topic, that how many number of atoms in one unit cell is over there in primitive, this is 1. On the basis of this number of atoms, we will solve our numericals. So the number of atoms calculating these are very, is there any problem? So the number of atoms calculating is quite important for every type of unit cell, okay? So please keep focus on this. And if you have any doubt or query, you'll ask me at the end of class. Okay, same as it is, if we are going to discuss with the body-centered unit cell, what would happen over there? Let me make a body-centered unit cell. I hope you have got this. Okay, now we have to calculate the number of atoms in unit cell that is body-centered. The same concept is over there. We have total 8 number of atoms which are shared. Okay, and the only difference in body centered is we have one center that is present in the center of a whole body of that unit cell. So first of all, if we have to calculate number of atoms, first point is 8 into 1 by 8. Why? Because 1 by 8 of atom belongs to this unit cell, I have already told. So 1, and second point is number of atom is present in the body, sorry, in the center of the body of unit cell. And the interesting thing, it is not shared by anything. Why? Because it is present in the center of the whole body. It is not surrounded by any kind of unit cell or any kind of other thing. Because it is present in the center, it is present in the safest zone. Okay, so it has complete one atom and it has complete share with this unit cell. So atom present in center of the body. I think now it is clear to you. So total number of atoms present in the body-centered unit cell, how would be equal to 1 plus 1 equals to 2. Okay, so this is quite easy and interesting topic, that in primitive unit cell we have just 1, but in body-centered we have 2. And the reason behind this is it is not shared by any kind of unit cell, whereas this atom, which is behaving like as a sphere, it is cut out by all the sides and all surrounded by 8 different unit cells. Okay, so in short, we can say that in body centered unit cell we have 2. Okay, now let's move to our last one, that is face centered. What's the logic behind this, and what's interesting and new thing is in the face centered unit cell? Let's see. In the face centered unit cell, we have already discussed that there are atoms present in the corner. That is the common thing, 8 present in the corner, and each face has 1 atom in its center. So each face has 1 atom in its center. We can behave like this. So total 6 atoms are present over there. First for the upper one and second for the back side. Okay. So there are total 6 atoms present in the face. So 8 into 1 by 8 equals to 1. This would be common for all the corners. Now we have seen that there are atoms present in the center of the face. We have total 6 face, and now tell me one thing, since it is behaving like a sphere and it is present in the center of the face, so it is shared by another unit cell. Suppose this is the upper front face, this is shared by another unit cell. So in actual, an atom that is present in the center of the face is shared by only half of that particular unit cell. So in short, I can say half of the atom which is present over the center, over the face of a unit cell actually belongs to it. Okay, this is an interesting point, and this is very point which needs to be understood. Okay, so in short, we can say total we have 6 faces, and since half of the atom actually belongs to, so we have 6 into 1 by 2, that is equals to 3. So 1 plus 3, we have total 4 number of atoms in face centered unit cell. Okay, I hope this is clear to you. So in short, what would we have? We have only 1 number of atom that is present in simple unit cell. We have number of atoms 2 present in body centered unit cell, and the same as it is, we have total number of atoms present in the face centered unit cell, which is equals to 4. Okay, so let me recapitulate this as a table which you can remember. Simple cubic unit cell, or also we can say it primitive, body centered unit cell, face centered unit cell, 1, 2, 4. These are the number of atoms present over. Okay, so this was the concept. These is that the reason behind this is that why I'm stressing this so much, because on the basis of number of these atoms that you will keep in your mind, you can solve the numericals based on the solid state, which you will get in your board exam or either in any kind of competitive exam. Okay, so for the board exam, this point is very important. Note this, only this. On the basis of this, the numericals are very important, which we will see after, I think, 2 to 3 more lectures. Okay, so this was the concept. Now let's move to another concept. Okay, let's start. Okay, now let's start with the another topic, close packed structure. Okay, I hope class I have made sense with this topic. You have to understand, you have got that how we have arranged the number of atoms present in a unit cell. which kind of unit cell have which kind of number of atoms. Okay, so now let's start with our next topic, that is close packed structure. Okay, in close packed structure, I have already told you that in the chemistry, we behave as we assume that all our atoms are behaving as a sphere. Yani we can assume them as a spherical atom. Okay, so now on the basis of this concept, let we try to make them in the close packing, because we know very well that our solids have completely close packed structure. This is the first basic unit, or we can say the first basic property of a solid state, that the solid state, the intermolecular force is so strong that they are closely packed. There is no difference, or we can say there is no space present between them. Okay, so on the basis of this one atom, we will step by step go from one dimension to two dimension to three dimension, and we will make a solid state. Okay, and whenever we go to from one step to two step to third step to make three dimension, in between we will see so many new terms which are very useful, and which are very useful for your concept and for your chapter also. Okay, so let's start with close packed structure in one dimension. Okay, in one dimension, we have only with this concept that molecules are arranged in such way. Since it is one dimension, that means there is only one direction, either it is x-axis or y-axis, either it is horizontal or vertical. So we are assuming that this is horizontal, and this is how our spheres are closely packed. Okay, this is the only representation. Now we are saying that let we assume this particular atom, and we will see that how many atoms are present in the neighbor of any particular atom. I'm again repeating, how many atoms are present in the neighbor of a particular atom, and this is known as coordination number. This is known as coordination number. So how many atoms are present in the neighbor of this? 1 and 2 only. Okay, but please keep in mind, this is one dimension. There is nothing upper and lower right now, only for one dimension. So the coordination number, which is defined as the number of atoms present in the neighborhood of a particular atom, which is equals to 2 for one dimension. Okay, all right, now let's move to two dimension. Okay, just give me a second. In two dimension, what would be the new concept? We are going to see the close packing as we have seen in one dimension. We are going to see close packing in two dimension. Let's assume this particular wave, this particular ray, in which we have closely packed our solids as closely as very close without any space, and as a sphere. Let's assume that this particular line is known as A. Okay, so we are having A present over there. Now in two dimension, we have two different directions. That means we have to put them horizontally as well as vertically. So let's put this line as well as another line over it. Okay, same as it is, just to make it complete and to make it in a direction like this. Directions and in two ways. Okay, that is A. Now, when I have assumed that I have made a stack or we can say a complete series in 2 dimension with the help of 1 dimension, what's happening over there? Let's assume this particular radius, this particular atom, and in 1 dimension we have to calculate our coordination sphere, that is number of neighboring atoms present over there. Same as it is, can you tell me how many neighboring atoms are present over there? Yes, this is 1, 2, 3, and 4. Okay, so the coordination sphere, coordination number equals to 4 over here. And since this is behaving like a square, because we have totally 4 different atoms present over there, and this is behaving like a square, so we are also saying it square close packing. Square close packing. Now the difference in 2 dimension is that it is basically of 2 types. When we have arranged our complete row, which we have assumed as A, one over another to make a complete stack, it was assumed by the scientists that it's in our hands, we can put a row A with another row in different direction, in different arrangement. And what would happen if we put these two rows in different arrangement? Would there be coordination number changed? Would there be close packing changed? Yes, and this is known as the second type of 2-dimension close packing structure. Let's see how it happens. The scientists have put another type of row with the same sphere, but in the different direction, and they have put some space between them. Like this, we have enough space left over here. They have done this in this way. They have said it, suppose it is B, and after putting a space, they have put it A, then B, then same as it is A. So they have put a new arrangement with BA, BA, BA arrangement rather than AA arrangement. This was first type of, now we have second type of structure in which we have just put out another direction. Okay, due to which our coordination sphere is now changed, the number of coordination number is changed, because now we have total 6 number of atoms which are attached to each other. Okay, that means now in this way we have just 4 number of atoms which were closely packed to each other, but here since we have total 6 number of atoms arranged with each other, so this is known as hexagonal close packing. This is known as hexagonal close packing. This is known as hexagonal close packing. And the coordination number would be here 6. Okay, we have made 1 dimension, we have made 2 dimension in the very same way. On 2 dimension and 1 dimension, we have put this row or first on this and then second on this. That would be little bit complex, but yes, we have to read that. The basis of this, we would make 2 type of voids known as tetrahedral voids and octahedral voids. What are these voids made and how are these voids made? Let's have a brief discussion which we will discuss in details in tomorrow's class. Just have a little bit, we can say, introduction of voids. See what's happening whenever we putting the 2-dimension structure and then I'm putting first row on the 2 dimension. What's actually happening? There is left a space between them. When there is a complete stack, when there is a complete closed packed 2-dimension structure, and I'm putting a one dimension row over it, what happens? There is some space left between them. Okay. See, whenever this space is left between them, this space is known as void. Some space is seen over there, but this is not so much visible because this is not completely two dimension, as my drawing is not so much good. Okay. But whenever we will make three dimension, I'll just try to put this and try to show them in your next class. There is some space left between them, which is known as void. Void means space. Void means empty space. Okay. And on the basis of space between the two direction, that is two dimension AAA and ABAB, with two different close packing, the square close packing and the hexagonal close packing. We have tetrahedral void and octahedral void, and on the basis of these voids we have numericals, which are very important for your board exam. So definitely we will see them in the very next class. Still now, please keep in your mind, we have just made two topics clear. The first topic is how many number of atoms are present in unit cell. That is 1 in simple unit cell, 2 in body centered, and 4 in face centered unit cell. Rather than we have discussed the close packing structure, we have said that we have assumed our atoms as completely closed sphere. Okay. And in one dimension, we have just put in one direction in which coordination number is 2. And then we have put them as AAA and ABAB. Due to which coordination number is changed each time, and we have different type of packing known as close packing, sphere close packing, and octahedral close packing. Okay, so this was all about by my side, class. If you have any kind of doubt in these topics, please ask to me, or otherwise we will just finish the topic. Sir, can we allow our students to unmute themselves? Because I think we're left with 7 to 8 minutes only. We have two different types. Okay, the first one was AA type and the second one was ABAB type. The only difference is the arrangement of the A type with the B type. See, A and B type are nothing different to each other. The only point is we have just shrinked out, we have just made the number of atoms less than the first side. Okay, the first point is this. So what happened whenever we put them in different arrangement? Okay, this is ABAB arrangement, and we have just done that in first row we have taken more number of atoms, and in the second row, which is adjacent to each other, which is adjacent to first row, we have taken lesser number of atoms. Okay, तो basically बच्चे ये ऐसा है कि suppose मैंने एक बार number of atoms ज्यादा ले लिए, so there is a bigger row, then there is the smaller row, then there is bigger row, then there is smaller row. Okay, due to which the arrangement would be disturbed. पहले क्या था, the arrangement was quite smooth because we have the same arrangement, we have the complete stack one by one. Okay, right now we have different type of arrangement due to different type of number of atoms. Okay, so अभी होगा क्या in ABAB arrangement? First, we have only 4 number of atoms which were in the neighborhood of a particular atom. But right now we have total 6 number of atoms. See, if I would make another concept, another row, that would be a little bit better. ABAB. Now, if we're taking as a coordination sphere, here were the only 4, but here are total 6. I'm saying my drawing is not so good, so please adjust with it. So I want to say that it is kind of like this one. Whereas in the first one, it was like a square. This seems to be a square and this seems to be a hexagonal. That means there is total 6 number of coordination number. Okay. So this is the difference between AAA and ABA. Okay, Vidhi? Is it now clear a little bit more better?